Hello and welcome to Lesson 8 of the GPS course. This will be about observing and processing. 3 surveyors and another guy. Yes, the presidents on Mount Rushmore, Washington, Jefferson, and Lincoln, all surveyors. Thought it was appropriate to put that up for this slide. The prospects of success the GPS project are directly proportional to the quality and training of the people doing it. More and more people believe that GPS is a matter of pushing the button and the answer will appear, when of course there's a good deal more to it than that if the answer is to be correct. The handling of equipment, reconnaissance, field logs, the inevitable last-minute adjustments, all require a good idea of what's going on for success. There are people who say that the operation of GPS receivers no longer requires qualified survey personnel, and that is true if all is needed is to push the right button at the right time. But that's as if everything goes as planned, which of course it almost never does entirely. And when there are difficulties, that's when it's important to know what is happening so that you can adjust. And conventional surveying and expertise have a place as well, because sometimes it is necessary, for example in offsets that we've discussed, to do a little bit of conventional work in a more optical way. But the bottom line is that GPS surveying requires some understanding of how the technology works. I mention safety equipment here because even though the more conventional type of surveying can be deterred by harsh weather, GPS really is not. And a rainstorm, a fog, or blizzard can not necessarily stop the GPS surveying. So it's important to have an extra eye towards safety when one is doing GPS. This page shows a observation schedule for a static control survey. And as you see here, the sessions are numbered as to when they start and when they stop, and then the receiver A, B, C, and D is shown and what station they are to be on and what they are to do when they move from one to another. This sort of a log is necessary when static surveying is done because, of course, the constellation needs to be observed simultaneously with GPS receivers occupying the points here. For example, receiver A on station 1, receiver B on station 3, C on 8, and D on 13 in session 1 need to be at that position beginning at 7:10 and stopping at 8:10 so that we will have a full hour of simultaneous observations on those stations, and then some reset and stay at the same place, and others move on to another station. For example, 1 and 3 reset, and station 8 and 13 move. Station 8 moves to station 2, station 13 moves to station 4, and then of course there's a half an hour given there for that move, and at 8:40 they all power up and observe till 9:50. This gives you an idea of how it is necessary to have the information of this well in hand when one does the work. Of course, this isn't the only kind of information that's necessary. Names, addresses, and phone numbers of property owners, combinations of locks, etc. have to be in place for the work to go smoothly. And this observation schedule can be revised, of course, if the observations don't go as planned. It should specify start and stop times, And in this way, the schedule will not only serve to inform every receiver operator of his or her own expected occupations, but those of every other in the project as well. And this is useful sometimes when unexpected occurrences cause a change in the schedule. Here we have an example of a station datasheet. This is the sort of information that will be recorded again in a static control survey to show the station that has been occupied, show a sketch of where it is located relative to other fixed landmarks, and then other information, how to reach it, and a description of the monument, and of course a signature and a date. The principles of good field notes have a long tradition, and they continue with GPS. A paper trail of this type is very useful when one needs to return to such a monument. Station datasheet can be prepared at any period, but perhaps the most usual times are during the reconnaissance of existing control or immediately after the monumentation of a new project point. Neatness and clarity, always paramount, are of particular interest when the station datasheet is to be later included in a final report to the client. The overriding principle in drafting a station datasheet is to guide succeeding visitors to the station without ambiguity. The station name fills the first blank. In this case, the vertical control station officially named S198, also serving as a project point, number 14, and that's why you see that on the top line. Horizontal control station is remonumented, and number 2 is sometimes added to the original name. Rubbings. The illustrated station datasheet provides an area to accommodate the rubbing. With the paper held on top of the monument's disc, a pencil is run over in a zigzag pattern, producing a positive image of the stamping. This method is a bit more awkward than simply copying the information of the disc onto the datasheet, but it does have the advantage of ensuring the station was actually visited and that the stamping was faithfully recorded. Such rubbings or close-up photographs are required by the FGCC standards. Photographs. The use of photographs is growing as a help for perpetuation of monuments. It can be convenient to photograph the area around the mark as well as the monument itself, and these exposures can be correlated with a sketch of the area. It's important to have, of course, an idea of exactly what the monument looked like if it's being occupied, to ensure that the one that is intended is the one that was occupied. It can be helpful to use the quad sheet name. One can put that on the station data sheet so that a mapping reference is available. The to-reach description is awfully important to be able to lead someone to the monument. The description of the route to the station is one of the most critical documents written during the reconnaissance. Even though it's difficult to prepare the information in unfamiliar territory, and although every situation is somewhat different, there are some guidelines to be followed. It's best to begin with the general location of the monument with respect to easily found local features. In this description, there's a road junction, a guard station, and local business. Now, of course, things change, and to-reach descriptions can become obsolete. But it is good to be as complete as possible and as specific as possible to guide someone to the actual location. The to-reach description should include mileages and travel times when they're appropriate. And if it's necessary to walk in, that should be shown. Land ownership is important, especially when consent is required. Reconnaissance parties should obtain the permission to enter the property and should inform the GPS observer of any conditions of that entry. It's also best to make special mention of any route that is likely to be difficult in tough weather. And of course, where helicopter accesses anticipated information about the duration of flight from point to point and the distance from landing sites is worthwhile. Now we are coming to the visibility diagram. Of course, it is awfully important to note that GPS observations require a good view of the sky. Obstructions above the mask angle must be taken into account, especially with static control surveying. This diagram is known as a station visibility diagram, or a polar plot, or sometimes called a sky plot. These concentric circles are meant to indicate 10-degree increments along the upper half of the celestial sphere. From the observer's point of view, 0 on the perimeter to the observer's zenith. The horizon would be 0 and the zenith would be 90 in the center. Hemisphere is cut by the observer's meridian, shown as line 0 in the north and 180 degrees in the south. In other words, if one were to look straight up, would be looking through the 90-degree point in the middle. The other numbers and solid lines radiating from the center every 30 degrees around the perimeter of the figure are azimuths from north, and augmented by dashed lines every 10 degrees. So, using a compass and a clinometer, this of course is a handheld device for measuring vertical angles, a member of a reconnaissance team can fully describe the possible obstructions of the satellite signals on the visibility diagram. By standing at the station and measuring the azimuth and vertical angle of points outlining the obstruction, the observer can plot the object on the visibility diagram. For example, here's a windmill base that is shown in the cross-hatched figure. It's been drawn from the observer's horizon up to 37 degrees in vertical angle, from 168 degrees azimuth to about 182 degrees. This allows one to correlate this obstruction with other charts that will give one the number of satellites available, the azimuth and height of those satellites at a particular time, and so design the observation on this particular point so that satellites will not be obstructed by this particular windmill. Knowing where it is allows you to design a session where there won't be obstructing satellites. This is a very good way to avoid multipath as well, since of course bounce of the signals from the obstructions can corrupt the observation. And here's an example of that sort of chart, the station or satellite azimuth and elevation table. For example, suppose a 1-hour session from 9:10 to 10:10 is illustrated was under consideration for observation on this station, S198. This is the one for which we saw the visibility diagram in the previous slide. The station visibility chart might motivate a careful look at Space Vehicle PRN 16. 20 minutes into the anticipated session at 9:30, SV16 has just risen above 15 degrees mask angle, and under normal circumstances would be available at station S198, but it appears from the polar plot that the windmill will block its signals from reaching the receiver. In fact, the signals from SV16 will apparently not reach S198 until sometime after the end of the session at 10:10. Under the circumstances, some consideration might be given to observing S198 during a session when none of the satellites would be blocked. However, the 9:10 to 10:10 session may be adequate after all, even if SV is completely blocked. The remaining 5 satellites will be unobstructed, and the constellation still will have plenty of low PDOP. Still, the analysis must be carried to other stations that will be occupied during the same session. The success of the measurement of any baseline depends on the common observations at both ends of the line. Therefore, if the signals from SV16 are garbled or blocked from station S198, any information collected during the same session from that satellite at the other end of the line that includes S190 will be useless in processing the vector between the stations. Well, that might be the end of it, but the material of the base of the abandoned windmill has been described in the visibility diagram as cross-membered steel, so it is possible that the signal from SV16 will not be entirely obstructed during the whole session. There may actually be more concern of multipath interference from the structure than from signal availability. It's always a good idea to avoid any kind of obstruction that can be avoided. For example, a chain link fence, like you see in this diagram, found hard against a mark, can cause multipath by forcing the satellite signal to pass through the mesh to reach the antenna. The elevation of an antenna over a fence with a survey mast is often the best way to work around that kind of an obstruction. But in this example, as you see in this photo, this concrete post that is right near the antenna can also cause, of course, multipath. An example of a long train moving near a project point could be a potential problem, but a vehicle passing by on a highway or a street usually are not, especially if they go by at high speed. It's important, of course, to avoid parked vehicles, and the best way to remind new GPS observers that the survey vehicle should be parked far enough from the point to avoid multipath. Just avoiding obstructions is, of course, a significant part of planning a good GPS observation. Of course, if one is going to use an offset, it must stand far away enough from the source of multipath or the attenuated signal to be unaffected. However, the longer the distance from the originally desired position, the more important is the accuracy of the bearing and distance between the position and the offset. Recording the tie between the two correctly is crucial to avoid misunderstanding after the work is complete. Some receivers allow input of the information directly into the observation recorded at the receiver or data logger. However, during a control survey, it's best to also record the information in a field book. Offsets in GPS control surveying are an instance where conventional surveying equipment and expertise are necessary. Clearly, the establishment of the tie requires a position for the occupation of the instrument and a position for the establishment of its orientation, an azimuth point, that is. It's best to establish 3 intervisible rather than 2 points, 1 to occupy and 2 azimuth marks. This approach makes it possible to add a redundant check to the tie. The positions on these 2 or 3 points may be established by setting monuments and performing static occupations on them all. But, of course, it's important to have the angle and the distance from the static GPS point to the obstructed point as indicated in the diagram. This all is designed to move an obstructed position away from the source of the difficulty to a place where the sky is visible. There's a wide variation in the kind of monumentation that is set for a GPS project. Some experts predict that GPS will eventually make monumentation unnecessary. The idea foresees GPS receivers in constant operation at well-known master stations and will allow surveyors with receivers to determine eye accuracy positions with such speed and ease that monumentation will be unnecessary. Well, we are moving closer and closer to that idea, as we discussed last time with the continuously operating reference stations. However, it is not entirely the case yet, and so monumentation does still remain an important part of establishing control with GPS. And here we have the network that we discussed last time, a static GPS network. When everything goes as planned, a GPS observation is uneventful. However, even before the arrival of the receiver operator at a control or project point, the session can get off track. The simultaneity of the data collected at each end of the baseline is critical to the success of the measurement. When a receiver occupies a master station throughout the project, there's a need for little concern on the subject, but most static applications depend on the sessions of many mobile receivers beginning and ending together. With proper planning and reconnaissance, an observer will likely find that there's enough time to make the trip from station to station, and sufficient information is on hand to guide him or her to the position, but it cannot be guaranteed. When an observer is late to the station, the best course is usually to set up the receiver as quickly as possible and collect as much data as possible. The baselines into the late station may or may not be saved, but they will certainly be lost if the receiver operator collects no information at all. And it is at times like these that good communication between the members of the GPS team are most useful. For example, some of the other observers in the session may be able to stay on their station a bit longer with the late arrival and make up some of the data. Along the same line, it is usually a good policy for those operators who are to remain on a station for 2 consecutive sessions to collect data as long as possible, while still leaving themselves enough time to reset. It's always important to center the GPS antenna over the station. Centimeter level accuracy of static GPS gives the centering of the antenna special significance. It's ironic that such a sophisticated system can be defeated by such a commonplace procedure. Unfortunately, the centering of the instrument over the station doesn't ensure that the phase center is properly oriented. The contours of equal phase around an antenna's electronic center are not themselves perfectly spherical. Part of their eccentricity can be attributed to the unavoidable inaccuracies of manufacturing. To compensate for this offset, it's good practice to rotate all the antennas in a session to the same direction. Many manufacturers provide reference marks on their antennas so that each one may be oriented to the same azimuth. That way, they are expected to maintain the same relative position between their physical and electronic centers when the observations are made. Remember that the phase center and the physical center of a GPS antenna are not exactly coincident. The antenna's configuration also affects other measurements critical to the success of GPS surveying: the height of the instrument. The frequency of the mistakes made in this important measurement are remarkable. Several methods have been devised to focus special attention on the height of antenna. It can be measured in both feet and meters, for example, and it can be checked just before moving the antenna on to the next point. And here is a diagram of the measurement of antenna height. It is measured in various ways to various points on the antenna or the receiver itself. The care ascribed to the measurement of antenna heights is due to the same concern applied to centering. GPS has an extraordinary capability to achieve accurate heights, but those heights can easily be contaminated by incorrect HIs, or heights of instrument. Here is the next log that is important, the actual observation log. Most GPS operations require the receiver operators to keep a careful log of each observation, usually written on a standard form. These field notes provide a written record of the measurements, the times, the equipment, and other data that explains what actually occurred during the observation itself. It's difficult to overestimate the importance of this information. It's usually incorporated into the final report of the survey. However, the most immediate use of the observation log is an evaluation of the day's work. An observation log may be organized in several ways. The log illustrated is one method. Of course, the name of the observer and the station is included. The date, expressed in both Julian, that's consecutive from the first of the year, and Gregorian calendars. That information can help in quickly cataloging the data. The approximate latitude, longitude, and height of the station are usually required. The date of the planned session will not necessarily coincide with the actual session observed. The observer's arrival at the point may have been late, or the receiver may have been allowed to collect data beyond the schedule of the end of the session. There are various methods used to name the observations. A widely used method is noted here. In this case, it is the point 14 and is designated 0014. The next 3 digits of the Julian day of the session. In this case, the day is 50, or 050. And finally, this session illustrated is the second of the day, or 2. Therefore, the full session name is 0014 050 2. Whether on board or separate, the type of antenna used and the height of the antenna are critical. And of course, one of the major reasons for this is that the distance between the antenna reference point and the phase center depend on the type of antenna. The distance at the top of the station's monument is found above or below the surface of the surrounding soil is sometimes neglected. This information can not only be useful in the later recovery of the monument, but can be important to the proper evaluation of photo control panel points. Weather is recorded. The meteorological data is useful in modeling the atmospheric delay. This information is required at the beginning and middle and end of the session of projects that are designed to satisfy the FGCC provisional specifications for AA and A orders of accuracy. A record of the satellites that are actually available during the observation, and any comments about unique circumstances of the session round out the observation log. Such observation logs are common and useful, necessary, I would say, in static control work. The plan of a GPS project usually changes daily. The arrangement of the sessions are altered based upon the success or failure of the previous day's plan, and some regrouping usually happens every day. The evaluation involves examination of the observation logs, such as we just observed, as well as the data received. Unhealthy data, cycle slips, multipath, other problems can, of course, cause an observation to not be successful. Some field supervisors prefer to actually compute the independent baseline vectors of each day's work to ensure that the measurements are adequate. Neglecting the daily check could leave unsuccessful sessions undiscovered until a survey was thought to be completed, and the consequences of such situation can be very expensive. Obviously, if a vector has failed, it's important to know it the very day it occurred so that it can be picked up in the subsequent day or days. Now, some of these methods, as I pointed out, are very useful, I would say necessary, with static GPS. However, RTK and DGPS differ. There are some things, such as the station diagrams, observation logs, and to-reach descriptions that would rarely, if ever, be necessary in such high production dynamic work. But there are aspects, though handled a bit differently, apply in both categories, whether static or RTK or DGPS. One such technique is the offsetting of points to avoid multipath. The need to offset points is actually much more prevalent in DGPS and RTK. However, the methods of dealing with it are more varied. DGPS and RTK surveying generally have lower accuracy requirements than does static control, and therefore the establishment of the tie between an offset and the originally desired position need not be so stringent. However, when circumstances arise that require a particularly accurate tie, the same conventional surveying may be necessary. Of course, the offset point must be established far enough from the original position to avoid any obstructed signal. While the calculation of allowable vertical and horizontal measurement errors can be done trigonometrically, the measurements themselves will be different than those for an offset point in a static survey. Rather than a total station point and an azimuth point, a magnetic fluxgate digital compass and a laser may be used to measure the tie, like we see in the upper left here of this slide. Of course, if such a magnetic fluxgate compass is available, one can get a magnetic azimuth, as indicated here, and measure a distance with the laser fairly conveniently, and have that offset recorded. The length of the tie may be measured by an external laser, a laser cable directly into the GPS receiver, or even a tape and a clinometer. Lasers, of course, are much more convenient since they can be used to measure longer distances more reliably than taping requires extra people. And rather than recording the bearing and distance in a field book for post-processing, in DGPS or RTK, the information is usually stored directly in the data collector. In fact, often the receiver's real-time processor can combine the measured distance and direction, the side shot that is, with the receiver's position and calculate the coordinate of the originally desired position on the fly. Dynamic lines. There is a technique unique to RTK or DGPS, and that is the creation of such lines as we see here, where there's an actual railroad that cannot be occupied, but one can actually walk along at a constant offset from this route and record positions at an interval. The GPS receiver typically moves along a route to be mapped, logging positions at predetermined intervals of time or distance, and these points can then be joined together to create a continuous line. Obstructions along the route present a clear difficulty, but it's doable to walk along a route recording positions at a set interval and then have a line created from it. While it is impossible or unsafe to travel along a line to be collected in the field, a dynamic line may be collected with a consistent offset. This technique is especially useful in collecting roads and railroads where it is possible to estimate the offset with some certainty due to the constant width of the feature. It is also possible, of course, to collect routes with individual discrete points of short occupation where that approach recommends itself. And now let's talk about a few procedures that might be useful in RTK and DGPS. As mentioned earlier, redundancy in RTK can be achieved by occupying each newly established position twice. And it is best if the second occupation is done using a different base than the first. It's a good rule of thumb to ensure that the GPS constellation during the second occupation differs substantially from that of the first. So it's best if the second occupation takes place not less than 4 hours and not more than 8 hours later than the first. To ensure that the centering is correct during the short occupations, it's best if a bipod is used and a fixed height rod to eliminate the possibility of an incorrect height. Concerning heights, if orthometric heights in real time are desired, a geodal model is required. Remember that. Because the heights derived from GPS are native in ellipsoidal form. However, please note that work retraced with a different geodal model than was used initially will likely show vertical differences in the reoccupied points. In RTK, there is a procedure known as a site calibration, which essentially is done to establish the relationship between latitude, longitude, ellipsoidal height, geographical coordinates, that is, and plane coordinates, northing, easting, and orthometric heights. Of course, using plane coordinates on an imaginary flat surface assumes a flat Earth, which is incorrect. But it's a viable simplification if the area is small enough. It's like the tangent planes that we discussed earlier. Such system demands little, if any, manipulation of the field observation once the coordinates are derived and can be manipulated with straightforward plane trigonometry. In short, it's Cartesian, it's simple, and it's convenient. However, difficulties arise as the plane grows larger. The axis, the scale, and the rotation of each one of the individual local systems will not be the same as those of its neighbor. Therefore, when a site calibration is done and a local flat plane coordinate is created, it's important to keep all the work in that system inside the limits created by the control points used in the creation of the plane. In the simplest case, a single-point calibration, a flat plane is brought tangent to the Earth at one point. But a more typical approach is the utilization of 3 or 4 control points enclosing an area. But it's good to keep the work inside the area defined by those points. Working outside of the limits created by the points means that the distortion hasn't been modeled. Now a couple of notes on using a processing service. There are actually several that are useful and available for post-processing GPS data that has been collected. And while they differ somewhat in their requirements, they're all based on the same idea. Static GPS data collected in the field may be uploaded to a website on the internet by a hosting organization, which will then return final positions, post-processed positions, often free of charge. Usually the user is directed to an FTP site where the results can be downloaded. There can be an advantage to using such a system. Aside from removing the necessity of having post-processing software in-house, there is the strength of the network solution available from them. In other words, rather than the data sent in by the GPS surveyor being processed against a single continuously operating reference station, let's say in the vicinity, it's processed against a group of nearest course stations. Remember, we discussed these continuously operating reference stations last time. There are often 3 that are used, 3 closest to the work that has been done. Such a network-based solution improves the integrity of the final position markedly and may compensate for long baselines required by the sparseness of the cores in the area of interest. Among the online resources available for processing, here we have an example, the Opus, our online positioning user service, and the website is given there. Again, this is for the download of static GPS files, and NGS will actually post-process them for you, free of charge, against the 3 nearest course stations. And here are others. The SOPAC, Scripps Orbit and Permanent Array Center, the Scout system, and of course AutoGypsy and OSPOS. Here are the websites, and in each case it is possible to submit GPS files for post-processing. Very convenient. Thank you for spending this time with me.